When most people think of artificial intelligence, they picture science fiction myths, conscious machines, or rogue neural networks. But modern computer science approaches AI through a much more rigid mathematical framework. To actually build an intelligent system, researchers have historically divided the field along two distinct axes of measurement. The vertical axis separates internal mechanisms from external results. Do we model internal thought processes or observable behavior? The horizontal axis represents success, measuring fidelity to human performance on the left and an ideal mathematical rationality on the right. This matrix shows 4 quadrants where every major AI approach fits. Human-centered approaches use empirical science, like Turing tests or biological cognitive models. Rationalist approaches discard imitation, relying on mathematics to calculate correct actions, ignoring biology. You cannot engineer a functional system by pursuing all 4 quadrants at once. To write actual code, computer scientists must choose one specific standard of success to optimize against. Human behavior is the product of a complicated and largely unknown evolutionary process. We are far from perfect. We are susceptible to systematic reasoning errors and limited by our inability to process millions of variables at once. This makes human biology an inconsistent benchmark for building reliable engineering systems. The quest for artificial flight succeeded when the Wright brothers stopped trying to build machines that flapped their wings like pigeons and instead focused on the underlying principles of aerodynamics. In that same way, modern computer science focuses on the underlying principles of intelligence, adopting a specific foundational axiom, the rational agent. An agent acts. A rational agent calculates available options and executes the action expected to achieve the best outcome. Here, rationality is mathematical consistency. Given its information, it does the right thing to achieve its goal. This provides a measurable, mathematically verifiable framework. We don't have to define consciousness. We just have to define the goal and engineer the logic to reach it. If the goal is to build a rational agent from first principles, the immediate engineering question is how to construct that logic. Historically, researchers started with pure philosophy. The Greek philosopher Aristotle made the first attempt to codify a mechanical process for generating valid conclusions, developing a system of strict syllogisms. He mapped a regression algorithm connecting knowledge to action. If you need a covering and a cloak is a covering, the logical output is to make a cloak. By the 1960s, computer programs executed these chains of deduction flawlessly within closed, perfectly understood environments.
However, the logicist tradition hit a massive hurdle upon contact with the real world. Reality is messy. You cannot easily codify informal, highly uncertain knowledge into the strict true or false notation required by formal logic. Pure logic is mathematically beautiful, but it fails as a comprehensive foundation for AI. A rational agent has to operate in a physical environment where information is always incomplete, and probabilities replace certainties. You might assume we could just brute force the problem, using massive computing power to calculate the precise probabilities of every possible action. But Alan Turing established a strict boundary on computation itself.
He proved there are some mathematical functions that simply cannot be computed by any algorithm. For AI, the specific mathematical wall is a concept called intractability, closely tied to NP completeness. When a problem is intractable, the time to solve it does not scale linearly, it grows exponentially. Even with a moderate number of variables, the decision tree expands so rapidly that solving it exhausts the finite memory and processing time of any computer. The real world is an infinitely large problem instance. Calculating every possible logical outcome of an action is physically impossible. Computational boundaries, rather than software limitations, define the barrier to perfect AI. Computation itself has physical and complexity-based limits that no amount of code can bypass. It is tempting to believe that hardware upgrades will eventually rescue us, that faster processors will simply outrun this complexity. This table compares the raw computational resources of a 2003 CPU against the human brain. The chip has a massive advantage in switching speed, executing instructions in nanoseconds. However, the brain compensates with structural parallelism, utilizing trillions of synapses simultaneously. Sequential processing speed is functionally useless when navigating the exponential complexity of real-world environments. A computer might think a million times faster in a straight line, but the brain processes information faster by evaluating thousands of paths at once. Since we cannot rely on infinite CPU speed or replicate perfect biological parallelism in silicon, we are forced to find a new mathematical framework for making decisions under hardware constraints. If we cannot compute the perfect optimal answer, we must change how we define a rational action. The tools for this shift come from economics.
John von Neumann helped develop decision theory, a mathematical framework that merges probability theory with utility theory. Decision theory allows an agent to calculate trade-offs. Even in environments with high uncertainty, the agent can assign a numerical utility value to the expected outcomes of its choices. But the pioneering researcher Herbert Simon realized that exhaustively calculating the perfect decision is a myth, even in human economic systems. He introduced the concept of satisficing. This is the mathematical model of making decisions that are computationally good enough, rather than wasting critical time and power chasing an impossible optimal choice. By importing economic principles, AI research stops seeking pure mathematical perfection and starts engineering practical, optimal trade-offs. Modern artificial intelligence is built directly on this intersection: philosophical logic, the strict limits of computation, and economic utility. This creates the architecture of a modern rational agent. First, sensory inputs feed into a probabilistic estimation. This state is evaluated by a utility function, applying satisficing to output a physical action. This synthesis is limited rationality, acting appropriately when constraints prevent exhaustive calculation. AI researchers prioritize the automation of optimal actions in a constrained reality over the creation of mechanical humans. Understanding AI requires moving past science fiction tropes and viewing the field as a practical integration of logic, mathematics, and economics.